It says, in a certain aspirin synthesis, 104.8 grams of salicylic acid was treated with 110.9 grams of acetic anhydride. And we want to calculate the percent yield if 105.6 grams of aspirin were produced. So often, if you're specifically trying to target the synthesis of one compound, when you do that, you put the reactants together. You don't often even measure the quantity of other products formed because your goal is not to make those. You would evaporate that compound or extract it or purify it through some chromatography technique to remove it from the final mixture. The idea is to get this in its pure form, this product that you're interested in. And that's not trivial. There's a lot of techniques that you can use to purify something, but it can often be more of a challenge than even making the substance. And if you're in pharmaceuticals or you're in chemical processing, it's really important to get something purified, because if you have these contaminants in there, those can cause problems for people who are using that product. So in this particular example, we're not worried about how to purify the product. This tells us the quantity of product we have made, so we would assume that that's pure, and that grams of product is not everything that you have at the end of the reaction. It's what the quantity of aspirin is after the aspirin has been purified. So if we want percent yield, that is the quantity, or that is the way to quantify the success of the reaction. Right? So how do you quantify the success on an exam? You would look at your percent, right? You see how many points there were you could have earned, and then you look at how many you earned out of that maximum possible. Just like any measure of success, you have to compare your performance to some standard. And so in the performance of a reaction, how successful the reaction is, we can't just say, oh, I made a bunch of products, so that was a successful reaction. Because we have to compare how much we made versus how much we could have made. So if I make 105.6 grams, that might seem like a lot. But if I put a huge amount of reactants in and I could have made 10 times that much product, and for some reason I only got 1/10 of what I could have gotten, that's not a very successful reaction. So the percent yield measures the success. And like on an exam, to calculate your percentage, you take the number you actually got, divided by the maximum possible, and multiply by 100. So that's what you would do for percent yield for a reaction. It's equal to the amount you actually got, which is the actual amount of product, which is called yield, how much product was yielded by the reaction, the actual yield, divided by the maximum possible amount of product you could have made. That's going to be determined by how much reactants you put in and how much I have, and when I run out of one, I won't be able to make any more product, so that will determine the maximum amount of product I can make. That's called the theoretical yield. So that will give me my answer. So I need both of those. So I've already got actual yield. It's telling me the amount I collected. That's the question. It tells me the actual amount of the aspirin that I made. So I can just plug that in right now if I want. Now I just need the theoretical yield, so I can divide and then multiply by 100. So the theoretical yield is tricky. Conceptually, students have trouble with it. Not sure why. It's just how much product could you make, maximum. If the reaction worked perfectly, and every bit of reactant I put in that could react, did react, and was converted into product, how much product would that yield? So in reality, you're never going to get 100% because some of the reactant molecules might not collide and undergo the reaction. Or some of the product, when you try to purify it and isolate it, might be lost along the way. So the amount you end up with in the end is never going to be perfect. It's never going to be everything you could have gotten theoretically. So that's why we calculate percent yield, to see how good the reaction was and how good our recovery was. So theoretical yield, it depends on the limiting reactant or reagent. The limiting reactant is whichever reactant I run out of first, right? Because if I have some random quantities of both of my reactants, and the balanced reaction in this case tells me it's going to react in a 1-to-1 mole ratio once I balance everything out. I mean, I would want to balance the reaction or make sure it's balanced. And when I balance it, everything here is 1-to-1. So my coefficients are all 1. So whatever amounts of these reactants I start with, if I happen to start with equal moles of both reactants, then since the balanced reaction calls for them to react in a 1-to-1 ratio, if I had equal moles of them, if I had like 5 moles of this and 5 moles of that, they should all react completely, and I wouldn't have any reactants left. In that case, in that perfect situation, both reactants would be limiting, because they're both limiting how much product I can make. But in reality, I realize if I'm working on a laboratory scale, if I put some number of grams of this in, I don't know the exact number of molecules. I can calculate the moles of this that I have, the 4 sig figs, but I don't know exactly how many molecules of that I've really put in, because there are billions and billions and billions of molecules in a gram of something usually. So what are the chances that I actually have enough of both reactants so they will react completely and I will have nothing left over of either one of them? Almost zero. I mean, it's basically zero. There's no way I can measure with that precision to make sure I have exactly the ratio of reactants that's exactly equal to the mole ratio of my reactants in the balanced reaction to give me 100% reaction. So what that means is no matter what I do, really one of my reactants will be limiting. And so this is really relevant to the next lab you guys are going to be doing, because you're going to be setting a reaction up like this and deciding how much reactants to put in. You realize that when you realize that you can't set it up so that all of your reactants are completely consumed, you want a strategy to think about, if I'm going to have a little bit of excess of one, even accidentally, which one do I want to have excess? Which one do I want left over at the end? Which one's easier to remove at the end? So in this case, the salicylic acid is a solid, and aspirin is a solid. So if I have excess salicylic acid in the end, it's going to be hard to get rid of it. All these two solids, they'll be mixed together. How do I tell which solid is which? And if I have the salicylic acid contaminating my aspirin, that makes it acidic. If someone takes that aspirin, it might upset their stomach because of the extra acid that's in there. So the acetic anhydride would make more sense to make that in excess, so that I have lots of extra. So if I had only 1 mole of this, maybe I use 1.5 moles of this, or 2 moles of this, or 3, so that there's lots of chances for the extra molecules of this to collide with the salicylic acid and get the salicylic acid to react 100%. So in most reactions, you intentionally don't use a ratio of the two substances that's necessary for everything to react. You might intentionally add excess of the reactant that's less expensive. If you're thinking about the economics, this is an expensive thing to buy. I want to convert it into aspirin. I don't want to lose any of it. I want to get all of it to convert to aspirin and get the maximum bang for my buck. So I might use extra of the other reactant to get it to react completely. So the idea in this calculation is, if at this point, if we're given starting quantities of my two reactants, I don't necessarily know which one I have extra of. Is it correct to say that whichever reactant I start with more grams of will be the one in excess? No, not at all. It totally depends on which one I have more moles of and what the mole ratio is in the balanced reaction. So this is a 1-to-1 ratio. So because it's a 1-to-1 ratio, if I did have more moles of this, then there would be an excess. But if upon balancing the reaction I realized that I had a 1 to 2 mole ratio, then I would need twice the moles of this to even react that completely. And so I would only have excess of this if I had more than 2 moles of it compared to every 1 mole of the other reactant. And so rather than worrying about that, we do a calculation to figure out which one we run out of first. So generally, there's a couple different ways to do that calculation. The way I like to do it is to say, kind of kill two birds with one stone. I'll set up one calculation to say how much products could I make if this reactant were to react completely. And so I'll do a calculation for that, and then I'll do a separate calculation. I'll say how much product could I make if this other reactant were to react completely. So I have two calculations. I need two calculations because at this point I don't know which reactant is limiting. I don't know which reactant I'll run out of first. So by doing those calculations, I find out which reactant I run out of first, and at the same time I'll find out when I do run out of that one, what's the maximum amount of product I could make, which is what I'm looking for the theoretical yield. So to set that up, I want to say how many grams of the aspirin this is the aspirin, could I make if all 104.8 grams of the salicylic acid were to react? Call that SA. You notice that when I put my units, grams, I include the substance. I noticed very few of you guys did that on the last exam, and there was a few conversions you were doing with molarity that got screwed up because you thought things were canceling that weren't really canceling. You can't cancel moles of one substance with moles of another substance. Moles cancel moles, but only if they're the same substance. And grams cancel grams, but only if they're the same substance. So I tried to emphasize that a lot, but to no avail. So maybe in the future you will start doing that. But so I have grams of one substance. I want grams, but for a different substance. So what we said last section was anytime you have information about one substance, you want information about a different substance, you've got to convert to moles first. So I want to cancel the grams of this substance and get to moles of that substance. The relationship between grams and moles is for the same substance, and I find that substance's formula and calculate that substance's molar mass. So the salicylic acid is the first one there. It's the C7H6O3. So I take 7 carbons plus 6 hydrogens plus 3 oxygens. And I get 138.118, just rounded to 138.12. Grams per mole, right? The molar mass is always the number of grams equal to 1 mole. So I've converted from grams to moles. The reason I did that was because if I want to relate one substance to another substance, it's the balanced reaction that tells me how to do that. The coefficients in the balanced reaction. So I can cancel 1 mole of salicylic acid. One of those is needed to produce 1 mole of aspirin. So often it won't be a 1-to-1 ratio. In this case, if you left out this step, it's not going to change the number mathematically because multiplying or dividing by 1 doesn't change it. But in most cases, you'll have different coefficients other than 1 here. And if you leave this step out, you won't get the right answer. So it's a really important step. It's the key step. It allows me to convert moles of a substance to moles of a different substance. Then if I want grams, then I would cancel the moles of aspirin and get grams of aspirin, and that is the molar mass. So now for aspirin, that has 9 carbons, so 9 times 12.01 plus 8 hydrogens plus 4 oxygens gives me 180.15 grams per mole. So when I cancel everything here, I've got this unit. So what I've just calculated when I multiply that through is that the maximum amount of product I could make is 136.7 grams of aspirin. But that's assuming that the salicylic acid is completely consumed and converted to aspirin. So that could be, that's reasonable, but if I don't do another calculation for the acetic anhydride, then I don't know if I could really possibly have even made that much, because acetic anhydride might be my limiting reagent. If I only have a little bit of it, I might run out of it first, and if I run out of that early in the process, that would limit me to the ability to make only maybe a little bit of aspirin. Maybe I can't theoretically make this much. Maybe this isn't the theoretical, maybe it's not the theoretical maximum, because if I run out of the other reactant early on, I won't ever be able to make that much. Right? That would be like, well, anyway. So I need another calculation. How many grams of aspirin if all of the acetic anhydride were to react? So I do the same type of calculation, just starting with a different substance. So this time I have acetic anhydride, and its molar masses have 4 carbons plus 6 hydrogens plus 3 oxygens. 102.09 grams of acetic anhydride per mole of acetic anhydride. Converting to moles because I want to convert from the starting information about acetic anhydride into information about a different substance, aspirin. So I find the coefficients that relate them. It happens to be 1 to 1. 1 mole of acetic anhydride can produce 1 mole of aspirin. And then I would use the same last step as I did in the last case, because I want to convert from moles of aspirin to grams of aspirin. So again, everything cancels except the grams of aspirin. So from the starting amount of acetic anhydride I have, I could have made up to 195.7 grams of aspirin. So I'm not going to put a box around that one because that one's not the theoretical yield. So the theoretical yield is the maximum amount of aspirin I can make. What this first calculation is telling me is that when I run out of salicylic acid, the maximum amount of aspirin I can make is 136.7 grams. I have enough acetic anhydride to make up to 195.7 grams of aspirin. But I can never make this much because I only have enough salicylic acid to make a smaller amount. So the salicylic acid is my limiting reagent. It's the reactant I have a smaller quantity of, but that limits the amount of product I can make to a smaller amount. And that's the maximum amount of product that I can make from this reaction. So this is my theoretical maximum. And that's what I put down here in my percent yield formula. That is the amount of aspirin I actually got divided by the maximum amount of aspirin possible. And so I divide that and multiply by 100, and I get 77.25%. So these units cancel. Right? A percent shouldn't have units because you're comparing an amount of something to the maximum amount of that same thing that you could have gotten. 77.25%, not great. So that person should probably improve their technique a little bit. This reaction is not a really difficult reaction. It's well known and worked out fairly well, but to gauge the success of the reaction, now if your percentage is really low, usually that's not very successful, but it could be. I mean, if you're doing a new reaction that's never been done, and you just need to make a little bit of the substance to test it for some anti-cancer properties or something, that if you get any of it, then you might consider that a success. So it's really dependent upon the type of reaction that you're trying to run. If you're running a reaction that's well known to work above 90% most of the time, then if you get less than 90%, it's probably not very successful.